Hello everyone. So the next topic is emitter follower or common collector. So common collector means you see the collector terminal is common for both input and output, right? So this is collector, this is emitter, and this is base, right? And this is RB. So and here this is an NPN transistor, so obviously the collector terminal should be at the higher potential compared to emitter terminal. So hence we have given a negative potential for the emitter terminal, and this is your RE, the RE or the load resistance for your circuit as well, right? So this is the common collector configuration, which is also called as emitter follower, because we are taking the output at the emitter terminal and hence it is emitter follower. So if we apply the KVL for this circuit in this loop, so I will redraw this circuit for the applying of KVL. So this is negative voltage, this is plus, this is ground, this is RB, and this is the direction of IB, right? And this is ground, this is collector, and this is RE, the direction of IE will be towards like this, right? And this is plus and this is minus, this is base and this is emitter, right? So if I apply KVL for this, see this is in the opposite direction, it will be minus IB RB, right? And this is plus and this is minus, so you have minus plus, you have minus VBE, and this is plus and this is minus for the current IE to flow through the resistance RE, so hence it is minus IE into RE, right? And here it is minus, so it is plus VEE is equal to 0, right? So here you are calculating the expression for IB, so hence what we do here, VEE is equal to IB into RB plus VBE plus IE is 1 plus beta times of IB into RE. So on solving for IB, you will get this expression as VEE minus VBE divided by RB plus 1 plus beta times of RE. So this is how you calculate IB, and ICQ you can calculate it with beta times of IB, right? So this is ICQ, and to calculate VCEQ you apply KVL to the output loop. So this is my direction of IE, which means this is plus and this is minus, and this is plus and this is minus for VCE. So I will start the other way around, so it is minus VCE, the KVL to output loop. So here KVL to input loop, okay? So minus VCE and minus IERE, and you have minus, so it is plus VEE is equal to 0, right? So hence your VCEQ will be VEE minus IERE. So this is how you calculate the VCEQ point for the emitter follower circuit, right? So we will take an example for the same, considering this RB as 240 kilo ohm and RE as some 2 kilo ohm, and beta you take it as 90, and VEE as 20 volt, that is minus 20 volt for this, right? So on solving for this, what you can get here is So on solving for this, we can directly find out the value of IB. So we have RE as 2K and RB as 240K, VE as 20 and beta as 90. So this IB, we will calculate it for IB. So IB equals 20 minus 0.7 divided by 240K plus 91 times of 2K, right? So on solving this IB, you will get around 45.7 microamps. So once you have IB, you can get ICQ, which is beta times of IB. Beta is 90 here, so 90 into 45.7 micro. So you will get ICQ as some 4.12 milliamps. So this is ICQ. Similarly, you can calculate VCEQ. So VCEQ is 20 minus, so IE and IC are almost one and the same, 4.12 milli into 2 kilo ohm, right? So on solving this, you will get VCE as around 11.68 volt. So this is VCEQ. So this is an example on emitter follower or common collector circuit, with which you can apply the KVL to the input loop and find out what is the value of IB. Once you find IB, you can find out IC, which is beta times of IB, and to find out VCEQ, you have to apply KVL to the output loop and you can find out VCEQ. And this is an example problem for the same, for which you will get ICQ as 4.12 milli and VCEQ as 11.6, right? So in the next class, we will discuss about common base configuration.